Hey guys, I'm Sam, that's the Sun Eater, and this is a YouTube channel where we look at how to use batteries and solar to add range onto an old EV. Today we're going to be looking at how to determine the capacity of these Leaf battery modules. These are the little components that are added together to make up the big battery pack that goes underneath this electric vehicle. And see if we can find battery modules that are in better condition than the old ones that are in the car that we may be driving, and swap those out to add range onto the vehicle. But before we jump into that, let's do our weekly update and look at the new solar records that we've set. Okay, so disregard these two wires hanging off there. That's part of the experiment that we're about to get into. We have set a new charging power record. That was 6 days ago. We hit 444 watts peak charging power, so that's pretty good, coming up on that half a kilowatt charging speed. And 4 days ago we set a new one-day solar power record of almost 3.2 kilowatts. So that's awesome. That's getting us close to the I'm pretty confident we can bring this whole system up to 4 kilowatts per day of peak solar. In my very first episode, I installed a charger to charge our batteries off grid power at night while the car is parked, and that wound up being a bad part for this project. It just charges too slow. I swapped it out for the IOTA charger that you can see right there that charges at about 700 watts. So I went back and I pulled out that Noco Genius. There was no reason to have that in there. I added this drain line for the AC. I didn't think that there would be, it's funny how much water there is in air. This AC unit right here only cools this small little cargo area, maybe 8 cubic feet behind the back seat, and I didn't think there would be that much water in such a small amount of air. But I didn't want to have an undeterminate amount of water just kind of dripping onto the floor of this compartment. So I added that little drain tube and hooked a water bottle up to it, and sure enough, on humid days you will get as much as like 12 to 14 ounces of water that drips out of there. So I just put a little water bottle underneath it, and it catches all that, and at the end of the day I can just dump it out. I also threw this little bin under here to put some frozen water bottles in, so that on days when it's really hot, like 100, 105 degrees outside, I can give this tiny little AC unit here that I'm asking so much of a little bit of help. Having said that, it does do a very good job of keeping this compartment cool. We've logged some temperatures already outside of about 90 to 97 degrees, and it can keep this compartment well under 80 degrees, probably around 75 degrees when we have it running. I hooked a kilowatt meter up so I could track how much power our AC unit is using, and I've gotten figures that range in between about 0.8 kilowatts to about 1.2 kilowatts, depending on how hot it is outside, how hard it's having to work. Okay, so we're setting new records in terms of peak charging power and the total amount of power in terms of kilowatts per day that we can get out of here. But we do have some bad news. I've been able to put 5,000, almost 5,200 miles on the car since I bought it, but I've lost one of my battery bars. When I first got the vehicle, it had 7, and now it's down to 6. And I have noticed some range loss. When I first got the vehicle, it would reliably go 45 miles on the freeway. If you went from a full battery to an empty battery, going 60 miles an hour, this vehicle would have gone about 45 miles. Now that number seems to be down to about 40. And that's very bad news for me, because that means that the vehicle will no longer have the maximum range that I need it to have to reliably serve as a commuter before I recoup all of my investment in the vehicle, in terms of the money that I saved on what would have been fuel and maintenance on the gas vehicle that I was driving before I started this electric vehicle experiment. I came across a really interesting anecdote of a guy over in Estonia who bought a Leaf with 200,000 miles on it, and it had its original battery in there. How on earth did that happen? This car only has 50,000 miles on it, and it has the same battery degradation as a car with 200,000 miles on it. I'll see if I can put a little link that'll pop up on the screen right here to that video if you want to go watch it. The reason the battery in my car is going downhill so much faster than the battery in his car is because of the climate where we live. In Estonia, the average air temperature is somewhere in the 40s, 41 to like 46 degrees. Here in Texas, it's probably 30 or 40 degrees hotter than that. That's both inspiring and disappointing news to me at the same time. It's inspiring because that tells us that the other components in the Leaf, battery notwithstanding, are fully capable of going hundreds of thousands of miles. The electric motors that power the drivetrains in these vehicles last. They last well longer than their gas engine counterparts. And if we can get a Leaf for $2,000 or $3,000 and figure out the battery problem, then we've got a vehicle that'll last hundreds of thousands of miles. That's the inspiring news. The sad news is that it really shows that how much potential is thrown away on these vehicles because Nissan never went through the trouble to install any kind of cooling system for their batteries. Is that something that we can go back and figure out some kind of DIY battery cooling system where we snake some kind of tube through the battery that pumps cool liquid through there and make these battery packs really last and see our investment back? I don't know. That would be a very interesting challenge. I think there's a company called Phoenix Power that's looking into doing a aftermarket Nissan Leaf battery cooling system so that we can start seeing these vehicles go 200,000, 300,000 miles instead of like the 50 or 60, the 60 or 70 that I might get out of this one before I have to replace the battery here in Texas. The information that people really need if they're considering a project like this with an old Leaf is they need to know about how fast they can expect to see battery degradation, loss of range per mile driven where they live at. So to that end, I'm going to start posting data on the capacity of my battery pack in this vehicle per mile driven, and I'm going to come up with a degradation per mile chart that I'm going to post. You can find a link to that graph on my Patreon page. I'll put the link in the video description, and you can go there if you're watching this 3-4 months from now, and I'm going to post data on the degradation per mile driven. How can I tell what the maximum capacity of my battery pack even is? Well, they make an app for the phone called the Leaf Spy app. When you download it, it looks kind of like this. You plug one of those OBD sensors, you probably can't see right there, into your vehicle. It communicates with the app on your phone, and right there you can see that we're at about a 90% state of charge, and we've got 10.8 kilowatt hours remaining. That turns into about 40 miles of maximum range if we're doing freeway driving. So the graph that I'll be making will be tracking the maximum capacity of the battery and therefore the range as it compares to the total miles that the vehicle is driven. And hopefully that'll give people who are considering a project like this the kind of information they need to make an educated decision on whether or not to pursue this project. Obviously, I have a horse in this race. I want this electric vehicle to be able to last tens of thousands of miles so I can more than recoup everything that I would have spent on gas and maintenance costs, cost of ownership in my old gas vehicle. But at this point, it's not looking real good. This may be the kind of thing where we have to go back and figure out this battery degradation system in hotter climates if we really want this vehicle to pay for itself and save us a lot of money. And that makes the engineering challenge even more significant. In spite of me having a horse in the race, as far as how I want the experiment to turn out, I will present the data as far as miles, battery degradation, all that, without bias, so that people who are considering replicating this experiment with their own electric vehicle and trying to refurbish an old EV can get a clear view of the facts without bias. I owe that to the subscribers and my own personal sense of integrity. Okay, that's it for the update. Let's go take a look at these Leaf battery modules. Regardless of how long we can limp along the battery that our old Leaf comes with, at some point we will have to either refurbish or replace that battery. Well, how do we do that? Well, we can buy new modules or entire complete battery packs straight from Nissan Those come at the rate of about $350 per module, or $7,200 for the entire complete pack. But if we're willing to roll up our sleeves and look at some used options, we can probably get something that'll work for much, much cheaper. But obviously, if we're getting a used one, it's already been in a car, it's already got some miles on it, it's already had some degradation. How can we determine the capacity of these used packs that we're buying? And how do we know how much range it'll add to our vehicle if we go through the trouble of swapping out those modules or complete packs? Let's take a second and learn about this battery module right here, and that'll give us some insight into what we can expect out of a replacement. Alright, this is a Nissan Leaf battery module. There are 48 of these inside the main battery pack underneath the car, all connected in series to give all the power that the motor and the AC and everything else in the vehicle needs. Each one of these battery modules has 0.488 kilowatt hours of capacity, right around half a kilowatt hour. And there's 48 of them, obviously, so you multiply that out, and you get 23.4 kilowatt hours of total power for the battery pack. Most people round it up to just 24 kilowatt hours. Now, inside of this battery module, there's actually two batteries stacked like pancakes, and this middle sensor right here is the voltage sensing terminal, and your battery management system for the vehicle, the computer inside the vehicle, has a sensor that connects to this that makes sure that the two batteries inside of these modules stay balanced. Now, the voltage of this battery right here varies in between 6.4 to 8.4 from fully discharged to fully charged. And if we multiply that by all 48 batteries in the vehicle, we find out that the vehicle battery voltage can vary from about 308 to about 403 volts at fully discharged to fully charged. Now, Nissan has a when the car tells you it's fully charged, it's not actually fully charged. The people that built it, in a somewhat futile effort to make the batteries last longer, put software inside the vehicle that cuts off charging when it gets to about 80%. That's because with all lithium batteries, it's the same way in your cell phone. When your phone tells you it's fully charged, the battery's not actually 100% full. It has software inside there that cuts off that charging. And that happens because most of the damage that's done to the battery happens when charging that last 10% or when discharging that last 10%. So whether it be an electric vehicle or a cell phone, anything that uses a lithium-ion battery has software inside there that limits, that keeps the battery from going below that final 10% or above that last 90%. So while in reality, the main battery for our vehicle could be charged up to 403 volts, that software actually cuts it off at about 384 volts, and that's the highest voltage you ever see in the Nissan Leaf battery pack. Chemically, this is a lithium manganese oxide with lithium nickel oxide metal battery. That is a more stable chemistry than the lithium cobalt oxide, I believe, that you find in like a cell phone battery or a Tesla electric vehicle. And because these batteries use that more stable lithium manganese oxide chemistry, it makes the Nissan Leaf battery much less prone to catching fire. People say it is inherently safer, and that really makes these things a favorite staple of DIYers. So as we pull these old modules out of our main battery pack and replace them with newer, less degraded modules and repurpose the modules that we're removing, it's nice to know that we're working with the most stable, kind of safest chemistry lithium-ion battery that we have access to. I intend to use the old modules that come out of this car in a kind of home off-grid power storage, but I'm getting ahead of myself there. That's enough of me blabbing about this module. How do we determine the capacity of this thing? Okay, the first thing we're going to do is hook up our watt meter to our battery. This device, the watt meter, analyzes the amount of power flowing into the battery. Additionally, because the 8.4 volt maximum that this battery works off is so low, you can very safely touch the two terminals. You're not going to shock yourself or whatever. Obviously, you don't want to short across these, so if you're working with something like a screwdriver, you want to make sure you don't accidentally touch that across both terminals, just because the battery will discharge at such a speed that it could hurt itself. But there's really no danger that you're going to shock yourself. And once we get our watt meter connected to our battery, the watt meter has a power supply, and you can see that it lights up. It's detecting 7.7 volts on the battery and 0 power flowing in or out of it. Okay, now the 6.4 to 8.4 voltage range that this battery operates over, that's kind of a weird voltage range to work with. They don't make a lot of chargers that are designed to operate in that range. So we are going to use a little voltage step down, or they also go by the name of buck converters. But if you just go on like Amazon.com and run a search on voltage step down, you can find several parts like this that range anywhere from only $10 to about $20. So what this does is it takes a more standard voltage source that we can find anywhere, like the 12 volt batteries. You know, I've got unlimited 12 volt power in the back of my car. You could also use just any standard car battery and hook it up to the voltage inside of this, and you will see that we are able to change the voltage output to anything we want. So we can take our 12 volt power and change it into 8.4 volt power to bring this battery up to full charge. And that's what I'm going to do now. I'm going to take my watt meter and connect the negative side to the negative output right there, and the positive side to the positive output. And then I will do the same thing over here with the positive and negative end. I will connect to my wires that I have connected to my positive and negative terminals of my solar battery bank. And once we get that hooked up, our little voltage step down comes to life, and it can see the 7.63 voltage that's detecting over here. Looks like there's some voltage drop across these wires, and now we just need to connect the input side to our battery bank. Okay, so now we have our 12 volt power source running through an adjustable voltage step down that we can turn this into any output power we want, and the voltage step down runs through the watt meter, and this will track the amount of power that flows into this battery, thus telling us the total capacity of this battery once it reaches the full 8.4 volts. So you can see that there is 0 amps flowing now at 7.63 volts. Let's grab our little flathead, put it in our voltage adjust right here, and turn this up to 8.4 volts, which is what we need to charge this battery. There we go. It looks like 7.9 is the highest it's going to go. The battery is basically absorbing voltage, absorbing power out of this at such a fast rate that this device is unable to generate that big difference in between the voltage of the battery and the voltage this thing's trying to put out, which also means this little guy right here is going to start getting kind of hot. So I'm going to plug a USB fan into our inverter, blow that on our voltage step down, and if we come over here, we can see that this guy, our watt meter, is starting to track the power flowing into the battery 8.3 amps, which is good. That matches what we saw on our voltage step down. And right here you will see a watt hours, 0.03 is what we're looking for. Okay, so here's everything set up. I've got my cooling fan running off my Guindel inverter, cooling this voltage step down, running through the voltage meter, and that's tracking all of our power that flows into this battery module right here. Using a setup like this, I mean, that meter is about $40 to $50. Those are 10 to 20, so for somewhere in between 50 to 60 bucks, we can charge any low voltage battery that we need to. We can adjust this voltage to pretty much anything we need to, I think up to like 20 volts, and determine the capacity of the battery by just observing the amount of power that flows through there. And as it charges, I'm going to come out here every hour or two, fire up my multimeter, and just test the voltage across the leads, make sure it's staying in a nice healthy range. We're at 7.73 right now, on our way up to I'll probably charge it to 8.3 volts. We'll be close enough to the maximum charge to give us a good capacity reading on this battery. After leaving this battery right here on this charging setup for several hours, I got it up to a full charge, which was about 8.3 volts. I then disconnected it, went back and tested the voltage on it a couple hours later, and it had fallen down to 8.2 volts, but that's still pretty much maximum charge. We're really not going to get a whole lot more power in this battery right now. So now let's double check the number that our watt meter gave us. I'm going to hook this battery up to a discharger that also tests its capacity. So I'm going to test its capacity on the way charging from 0 to full, and I'm going to test its capacity charging from full down to 0, and that'll give us a very accurate number as to what the capacity of this battery is. Okay, so we got this guy over here on the charging rig. This battery's already been fully charged to 8.3 volts, and then it kind of fell back down to 8.2, but it's really at about 99% charge. Now we are going to hook this battery up to our battery discharge capacity tester. Now this device needs an external power source to run the CPU, so we've got that plugged into our inverter as well. Everything out, the whole experiment is solar powered right now. And after we hook this device up, we can see we've got the watt hour counter right there, the voltage of the battery, the amps flowing out of it, and these two knobs over here will allow us to adjust our discharging amperage. And it's just going to take power out of that battery and run it through a resistor and slowly discharge that battery that way, and tell us exactly how much power it's pulling out of there. I'm going to dial it up to about 3.3 amps there, which is, you can see, so it's discharging this battery at about 27 watts or so, 26, 27 watts. It's starting to count up the watt hours that it's pulling out of there. And I've got this battery set to this discharger. I have set to stop discharging at 6.5 volts, which is only 0.1 volts above the absolute floor that this thing can safely go to. So that will do its thing. And using this this method, we can test the capacity both on the discharge and on the charge cycle, get a real good look at exactly what the capacities of these used modules are, and always run it through a few cycles too. A battery can kind of get, I don't know what the chemical explanation for it is, but it gets stagnant when you leave it on a shelf for a while, and it won't give a true reading of its capacity on the first charge-discharge cycle you run it through. You run it through 2 or 3 of those, and then it will give you a more accurate read on what its actual capacity is. So I'm going to run this cell right here through 3 charge and discharge cycles and come back to you guys with the results of that test and see what the capacity of this battery module is. Okay, here are the graphs of the data that I got from running the battery bank back and forth from about 95% discharged to about 95% charged 4 times. I should have got more data points at the very beginning and very end of the cycles, so you can see where the voltage really falls off a cliff as you go below 7.5 volts and spikes sharply above 8.10 volts. I'll superimpose a professionally done lithium battery discharge chart here so you can see those cliffs more clearly. While I did see some increase over the cycles in the maximum capacity that these modules could hold as I cycled it a few more times, I was overall pretty disappointed with how these modules performed. Why? Battery hookup indicated that their tests showed capacities of 75 to 85% for these modules. Let's go with the low end of that estimate. 75% of this 488 watt hour battery should be 366 watt hours. Once again, that's the low end of their estimates, 366. But my tests never even broke about 280 right here. That's almost 20% shy of their estimates. Maybe the battery I got was an outlier. I'll cycle it a few more times and I'll see if I can get a capacity increase. And then I'll go test the other battery that I got from them. But as it stands now, it looks like these modules are significantly underperforming what their estimates were. Okay, so these are not our 85% battery modules that we were looking for. But let's muse for a second on what we could do if we could get a dozen battery modules at $50 a piece, the price I paid for these, that had 85% capacity or more. That would be $600 for the dozen of them. My battery in the Leaf is down to a 50% state of health, so that would be a 35% increase going from the 50% battery modules in there to the 85% ones if we could source those. Well, a 35% increase times a 488 watt hour battery turns into 170 watt hours per battery. If you multiply that out by all 12 batteries, you get 2.04 kilowatt hours, which turns into about 9 miles of range or so. So if we're only losing 5 to 7 miles of range a year, we can erase an entire year's worth of battery degradation for only 600 bucks. That comes out to about $50 a month, or well less than we're spending on gas and oil, plus the 12 modules that we pull out of the Leaf and replace with the new ones just became essentially a free home battery bank that we can use. It's not a bad deal, but it hinges on us being able to find a reliable, cheap source of lightly degraded used Leaf battery modules. So I'll keep looking. If I come across anything promising, I'll post it in the comment section of this video. If you know a good source of lightly degraded battery modules, please feel free to post there as well. I'm going to be hunting for some good ones and saving them up for the battery refurbish video that is inevitably going to happen in the next year or year and a half on this channel if I want to be able to continue to drive this vehicle. Now you know how to determine the capacity of your Leaf battery modules, and you know how much range you can expect to add onto your EV by swapping them out. Let's go ahead and take a look at the economy V of the week. Well, there's an economy V if I ever saw one. Look at that beaut. This dude chose the wrong time to check his Facebook feed. So we talked a lot this episode on sources of cheap, almost new batteries, and I would be remiss for not mentioning a very common go-to for DIYers, the junkyard. This 2013 Leaf has relatively low miles, 37,000. The snow in the pictures is a good sign, because those batteries do better in the cold. And even though she's got a few dings on the front bumper, wherever that is, the vehicle still turns on, and the battery has 11 out of 12 battery bars. It's almost in mint condition. The seller is asking under $3,000 for the battery, and plus it'll cost you about $300 to ship it from Michigan. For those who prefer their airbags non-deployed, I found this fully loaded 2013 Leaf. It's got a heated steering wheel, leather seats, all the options. Only 39,000 miles on the odometer, and all 12 battery bars. The car really is in like-new condition for $7,500. It's not the cheapest EV I've ever seen, but it's definitely a fair deal. Alright, that's going to be a wrap. Thank you guys again for tuning in and supporting the channel. Feel free to track the battery degradation of my Leaf on the Patreon page, and I'll see you guys next time.